So what exactly is binary classification? Well, it's a task where we classify data into one or two categories. For example, given an image, we might want to classify it either as a cat or it's not a cat. Sounds simple, right? But there's a lot of fascinating math and coding behind the scenes to make this work. Let's set up the problem. Imagine you have an input image. The goal is to assign a label 1 for cat and 0 for non-cat. To make this happen, we represent the image as a feature vector, which is essentially a numerical representation of the image's pixel intensity value. Here's how that works. We'll start by representing the input data X as a matrix. Each column of this matrix corresponds to one training example, and each row corresponds to a feature. So for an image, each feature represents a pixel intensity value across the red, green and blue color channels. As you know, images are made up of three channels: red, green and blue, that is the RGB. For example, if your input image is 64 by 64 with 3 color channels, you will have a total of 64 times 64 times 3, that is 12,288 features. That's a lot of numbers. These feature vectors become one column in our X matrix. Similarly, the labels are stored in a vector. Each element in Y corresponds to the label of the respective training example in X. For example, if you have 3 training examples, Y might look like this: 1, 0, 1, which means that the first and the third image with the 1 output, it means that it is cat, and the second with the 0, it is not a cat. Okay, let's look at the image example once again with this with the help of this drawing. So as we have discussed earlier, in the images we have for the color images we have 3 channels: red, green and blue. So as you can see in the diagram below, we have 64 by 64 image here. So it will be 64 cross 64 for one channel. Then again we have the same data number of data for the green one. So the green one will also have 64 cross 64, right? And then for the blue also we will have 64 cross 64. So the total number of data here, it will be total feature data, we can say that total feature data will be 64 cross 64 cross 3, that will be 12288, that is 12,288 data. So here what does each data means? That means the pixel intensity at that particular point. So as we can see in the red, it starts with 255 as the first value, 234 as the second, 264, then goes on to 288. Similarly, we will have all the other data stacked up here for the red ones, and then for the green ones, and then similarly for the blue ones. So let's see how we will stack this up for the X data here. The feature vector becomes one column in our X matrix. So it start with the red data, that is it start with 255, then 234, 264, 288, and it goes on for all the red data. Then it will start with the green ones: 244, 243, 242, 241, and for all the green data. Then after that it will go for the blue ones, then 234, 232, 231, 230, and so on for the blue ones till all the data of that particular image is in the X matrix. So as you can see, we can visualize how does our input look like. Right now it looks like a column vector. So let's figure it out. How does our Y, the output, will look like? So for the output we will use the Y's character. Similarly, the labels Y are stored in a vector. Each element in Y corresponds to the level of the respective training example in X. For example, if we have 3 training examples, then Y might look like this. For the first example, the value is 1, that means yes, it is a cat. For the second one, it means 0, that means that it is not a cat. For the third, the Y value is 1, that means yes, it is a cat. So this is how our feature vector becomes one column in our X matrix, and how does the y looks like for our data. Okay, let's look at the notation that we will use throughout the videos. So for a single training example, we will use x comma y to denote that, and the x will be of dimension nx. So for a single training example, it will be like this. Let's say x1, it will be like this. Here it will be like x11, x12, x13, and go on. It will go on till x1 and x, like this. uh, Similar kind of thing, but you got my point, right? So there will be nx dataset over for a particular single training example. So how does y look like? So y will be a single value. It will be either 0 or 1. So this is how we will represent a single training example. So now let's see how does m training example will look like. So we will take m training examples, right? So we can simply write it as x1 y1 single training example, then we will go to x2 y2 for the second example, and so on till xm then ym. It will go on till this. So also we can stack all the training examples together and all the output, the labels together. So for that we will use capital X to denote that, and we will simply stack it like this: x1 x2 till xm, and uh, the dimension will be m for m training examples, and each will be of nx dimension, and so on. For the xm example also, it will be of nx dimension. So all of will be nx dimension. So for this we can write it as, so the x will be of shape nx by m, and while doing the code we can simply write it as x dot shape, and it will come as nx comma m. When we write the code, you can simply just type this, and we can see the different shapes of the matrix that we will formulate. So now let's see how does our levels look like. For level we will simply denote it with capital Y, and with Y we can simply write it as y1 y2 dot 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 then ym. So as we have seen in our previous videos also, it will simply be one number like 0 or like 1, or again it will be either 0 or 1, or simply like that only. So it is a simple row vector, and it will have the shape of 1 cross m for m training example. As you can see, we have m training example that so that's why its shape will be, if we do y dot shape, then we can simply see that it will be of 1 comma m. So when I will write the code, I will just show you all the steps of the different metrics and all, so that we can more easily visualize what kind of data that is going inside our model. Okay, as we know that nx represents the number of features or the size of each feature vector, and m that represents the number of training example. So our input matrix x will be of shape nx comma m, and our label matrix y will be of shape 1 comma m. So in Python we can check this by using the dot shape attribute. Let me show you how we can see this in code. So yeah, let's start by importing the necessary libraries that we will use. So starting on, we will use numpy. So let's import numpy by import numpy as np. Then we will simply define the constants that we will use. For now, let's make this a bit simpler with small matrices and small shapes. So for now, let's define the constants. So the dimension of each training example, that is the feature. Let's say we have 5 features, so nx will be 5, and let's say we have 3 examples for now, then m will be 3. So we have defined the number of features that we will have for each training example, and the number of training example, that is 5 and 3 respectively. Now let's just generate some random numbers that we will insert into the nx and m. So we will run the first block of our code, then we will start with the second block. For the second block, let's start by generating some random data for our matrices. We will start with x, the capital X. The matrix X contains random feature values and it's of shape 5 comma 3, that is nx comma m, meaning we have 5 features for each of the 3 training examples. So for that we will simply use numpy library for this. Then we will use capital X equals to np dot random dot rand, and then inside the braces we will give the shape of the matrices that we want to create. It will be nx comma m. So after that we can also print this particular matrix so that we can know what kind of data is being created. So you can see that over here we have m, that is 3 training examples in each column. So this is the first example, second example, third example, and for each example set we will have 5, and that is nx examples, that is 1 2 3 4 and 5. So we will have 5 examples. So now let's create the y, that is the labels for our training examples. So now we will again generate some random output labels. So our output labels should be of shape 1 comma m, where each entry is either 0 or 1. For that we will simply use np dot random dot rand int. Then we will open our curly braces, then we will use 0 comma 2, then size will be from 1 comma m. Now let's print this and see how does this look like. So as you can see, it is 0 1 1. That simply means that yes, it is not a cat, yes it is a cat, and yes it is a cat. That is our example that we have been following till now. So I'm just showing it to you. By structuring our data this way, we are preparing it for logistic regression, which we will learn to classify input based on the relationship between x and y. But before we dive into the math behind logistic regression, let's quickly summarize what we have learned so far. In this video, we have introduced the concept of binary classification and explored how to structure the data for a logistic regression model. We saw how to represent images as feature vectors in the X matrix. We learned how to organize labels in the Y vector. And finally, we used Python to create random training data and reviewed the shapes of our matrices. In the next video, we will dive deeper into logistic regression. We will explore the math behind it, learn about the sigmoid function, and implement the forward pass. Make sure to stay tuned. Thanks for watching this video. If you found this video helpful, please give it a thumbs up and share it with your friends. Don't forget to subscribe and leave a comment below if you have any questions or suggestions for future videos. See you next time and happy coding. Bye.